Hi guys, so in today's video we'll be discussing introduction to simulated annealing. Simulated annealing is a powerful optimization technique inspired by the physical process of annealing in metallurgy. It is a versatile algorithm that can be applied to a wide range of optimization problems, from scheduling and routing to design and engineering. The key idea behind simulated annealing is to explore the search space in a controlled and deliberate manner, allowing the algorithm to escape local minima and find the global optimum solution. This approach mimics the way materials are heated and slowly cooled to achieve a low-energy crystalline structure, making it a highly effective tool for tackling complex, multi-dimensional optimization challenges. In other words, simulated annealing is an optimization technique used to find the best solution to a problem. It's like trying to find the lowest point in a landscape with a lot of hills and valleys. Imagine you are blindfolded and placed in this landscape. You start at a random point and begin moving around, trying to find the lowest point. But instead of always moving downhill, you sometimes take a step uphill, even though that might seem like the best move. The reason for this is that the simulated annealing algorithm allows for some uphill moves in the beginning to help avoid getting stuck in a local minimum. That's a valley that's not the deepest one. The annealing part refers to the way the algorithm adjusts the probability of taking uphill steps over time, just like how metal is annealed, that is heated and cooled, to become stronger and more stable. Optimization problems and challenges. We have complex search spaces, we have rugged objective functions, we also have constraints and feasibility. Under complex search spaces, many real-world optimization problems involve vast multi-dimensional search spaces with numerous local minima and constraints. Traditional optimization methods often struggle to navigate these complex landscapes effectively, leading to suboptimal solutions. Under rugged objective functions, optimization problems can have objective functions with many peaks and valleys, making it difficult to find the global optimum. Simulated annealing is well suited to handle these rugged landscapes, as it can explore the search space more thoroughly and avoid getting stuck in local minima. Constraints and feasibility. Real-world optimization problems often have a variety of constraints, such as resource limitations, safety requirements, or regulatory guidelines. Simulated annealing can be designed to handle these constraints and ensure that the final solution is feasible and practical. Steps under the simulated annealing algorithm. 1. Initialize. The algorithm starts with an initial solution and an initial temperature parameter, which represents the level of exploration allowed in the search space. 2. We have generate neighbor. At each iteration, the algorithm generates a new candidate solution or neighbor by making a small, random change to the current solution. 3. To evaluate. The algorithm then evaluates the objective function of the new candidate solution and compares it to the current solution's objective function. 4. Accept or reject. based on the acceptance probability, which is determined by the temperature parameter. The new candidate solution may be accepted even if it's worse than the current solution, allowing the algorithm to escape local minima. 5. Cooling. The temperature parameter is then gradually decreased, reducing the likelihood of accepting worse solutions and guiding the algorithm towards the global optimum. And 6. Repeat. The process of generating, evaluating, and accepting or rejecting new solutions continues until a stopping criterion is met, such as a maximum number of iterations or a sufficiently low temperature. Analogy to annealing in metallurgy. Heating and melting. In the physical process of annealing, a material is heated to a high temperature, causing the atoms to break free from their crystalline structure and become a disordered molten state. Slow cooling. The material is then slowly cooled, allowing the atoms to gradually rearrange themselves into a low-energy, stable crystalline structure. This process minimizes defects and maximizes the material's strength and resilience. Analogy to optimization. The simulated annealing algorithm mimics this process by starting with a high temperature that allows the search to explore a wide range of solutions and then gradually reducing the temperature to focus the search on the global optimum. Escaping local minima. Just as the high temperature phase of annealing allows atoms to break free from local energy minima, the simulated annealing algorithm can occasionally accept worse solutions, enabling it to escape local optima in the search space. Acceptance probability and temperature. 1. Acceptance probability. The simulated annealing algorithm uses an acceptance probability function to determine whether to accept or reject a new candidate solution. This probability is based on the difference in objective function values between the current and candidate solutions as well as the current temperature parameter. 2. We have temperature parameter. The temperature parameter controls the exploration-exploitation trade-off in the algorithm. At high temperatures, the algorithm is more likely to accept worse solutions, allowing for a broader exploration of the search space. As the temperature is gradually reduced, the algorithm becomes more focused on exploiting the most promising regions of the search space. 3. Exponential cooling. A common cooling schedule used in simulated annealing is the exponential cooling schedule, where the temperature is reduced by a constant factor at each iteration. This allows the algorithm to start with a high level of exploration and gradually transition to a more focused exploitation of the search space. 4. There's convergence. As the temperature approaches zero, the acceptance probability also approaches zero, and the algorithm becomes more likely to accept only improvements to the current solution. This gradual convergence towards the global optimum is a key feature of the simulated annealing algorithm. Exploring the search space. There's initial exploration, there's gradual focusing, and there's controlled convergence. Talking of initial exploration, at the beginning of the optimization process, the simulated annealing algorithm is more likely to accept worse solutions, allowing it to explore a wide range of the search space and avoid getting trapped in local minima. And the gradual focusing. As the temperature is reduced, the algorithm becomes more focused on exploiting the most promising regions of the search space, refining the solution and converging towards the global optimum. And under controlled convergence, the careful balance between exploration and exploitation, guided by the pooling schedule, allows the simulated annealing algorithm to efficiently navigate the search space and find high-quality solutions even for complex optimization problems. Cooling schedules and convergence. There is temperature reduction, convergence criteria, cooling schedule strategies, as well as parameter tuning. Under temperature reduction, the cooling schedule, which determines how the temperature parameter is reduced over time, is a critical component of the simulated annealing algorithm. The choice of cooling schedule can significantly impact the algorithm's performance and convergence. Talking of convergence criteria, simulated annealing algorithms typically use a stopping criterion, such as a maximum number of iterations or a sufficiently low temperature, to determine when the optimization process has converged to a near optimal solution. Cooling schedule strategies. Common cooling schedules include linear, exponential, and logarithmic cooling, each with its own advantages and trade-offs in terms of exploration, exploitation, and convergence rates. Parameter tuning. Effective implementation of simulated annealing often requires careful tuning of parameters such as the initial temperature, the cooling rate, and the neighborhood generation mechanism to achieve optimal performance for a given optimization problem. Now we talk of advantages of simulated annealing. We have global optimization. There's also versatility as well as simplicity. Simulated annealing is particularly well suited for finding global optimal solutions even in the presence of numerous local optima. Its ability to escape local minima makes it a powerful tool for tackling complex, non-convex optimization problems. Versatility. The simulated annealing algorithm can be applied to a wide range of optimization problems, from scheduling and routing to design and engineering. Its flexibility allows it to handle various objective functions, constraints, and problem formulations. Simplicity. Compared to some other optimization algorithms, simulated annealing is relatively straightforward to implement and understand. Its core concept of gradually reducing the exploration-exploitation trade-off is intuitive and easy to grasp. Applications of simulated annealing. Simulated annealing is applied in combinatorial optimization, also applied in engineering design, network and transportation, including machine learning. Simulated annealing has been successfully applied to a variety of combinatorial optimization problems, such as the traveling salesman problem, the job shop scheduling problem, and the knapsack problem, where it has demonstrated its ability to find near optimal solutions. Talking of engineering design. In engineering, Simulated annealing has been used for tasks like circuit layout optimization, structural design, and material science, where the algorithm's flexibility and global optimization capabilities are particularly valuable. Network and transportation. Simulated annealing has also found applications in network routing, traffic optimization, and supply chain management, where it can help find efficient solutions to complex logistics and resource allocation problems. Under machine learning. In the field of machine learning, simulated annealing has been employed for tasks such as hyperparameter optimization, feature selection, and neural network architecture design, demonstrating its potential to improve the performance of various learning algorithms. Thank you for joining me in this discussion. See you next time. Bye.